Let's look at some trends in the periodic table. The first trend we'll consider is atomic size. Atomic size is sometimes known as atomic radius. It is the size of the atom. We know that as we move from top to bottom down the periodic table, we go from the first period elements to the second period elements to the third period, etc. The principal quantum number, n, is increasing. Because we know that hydrogen and helium are in the first period and have a principal quantum number of n. Lithium through neon are in the second period. Their principal quantum number is 2. Sodium through argon are in the third period. That's their principal quantum number, etc., etc. So as we move from top to bottom on the periodic table, the size increases top to bottom. So what we're saying is that rubidium is going to have a larger atom than lithium. An atom of rubidium would be larger than lithium. What happens as you go from left to right? Which one would be bigger, lithium or fluorine, for example? Well, as you go left to right, size decreases left to right. So fluorine would be smaller than lithium, and I could write that like so. Fluorine is smaller than lithium because I'm looking at atomic size. Why would that be? Why would fluorine be smaller than lithium? Well, because fluorine has a much more positive nucleus. It has a +9 on its nucleus, whereas lithium only has a +3, and so that nucleus has a greater pull on the electrons. And that's the trend for atomic size. What about ion size? Well, if we go back, consider how does an atom become a cation? In order to become a cation, electrons are lost. And if you'll recall, in learning about the sizes of the atom, electrons make up most of the space of the atom. The nucleus, where the protons and the neutrons are, is very, very small. So the nucleus doesn't have a lot to do with the size of the atom. It's the electrons. So when you lose electrons, it's going to become much smaller. So cations are always smaller than their neutral atoms. In other words, what this is saying is that a calcium is larger than a calcium ion. The ion's smaller because it's lost electrons. And so if we could take that and turn around, what's it going to mean for anions? Well, in an anion, we know that electrons have been gained, and adding electrons is going to increase the size. So anions are always larger than the neutral atom. So we might write that and say that a fluoride ion is larger than a plain old atom of fluorine. The next trend we'll look at is ionization energy. Ionization energy is the energy required to remove an electron. How easy is it to take an electron away? Well, if we look, say at the first period, lithium versus cesium. Which one do you think it would be easier to remove an electron away, to take an electron away? It's easier to take an electron away from cesium. So what we say is that it decreases top to bottom. Why does it decrease top to bottom? Well, it goes back to size. A cesium atom would be larger than a lithium atom, so the electron you're taking away is much further from the nucleus. And it's the pull of the nucleus is what hangs on to the electrons. So it decreases top to bottom, and that makes sense if we think of it in terms of the elements at the bottom are larger than the elements at the top, so it's easier to remove an electron. So what about left to right? Left to right, it becomes more difficult to remove an electron. And hopefully that also makes sense, because we just said when we were looking at atomic size that atoms become smaller left to right. That means those electrons are closer to the nucleus. So they're closer to that positive charge. They're hung on to tighter. So it becomes more difficult to remove them away, to take electrons away as you go from the left to the right. And the last trend that we'll consider is electron affinity. Electron affinity can sort of be thought of as the opposite of ionization energy. In ionization energy, we're removing an electron. Electron affinity is the energy changed when an electron is added. Electron affinities generally decrease from top to bottom. And they generally increase as you move from left to right. When you consider all of these trends, whether it's electron affinity, ionization energy, atomic radius, or ionic radius, these are just trends. There's always exceptions. And so sometimes you could encounter exceptions to these, especially when you enter into the transition metals. So remember that these trends apply to the representative elements. What are the representative elements? These trends do not apply to the transition metals, just the elements that flank those on the outside of the periodic table, the representative elements.